So previously we finished up to this point, ReLU, huh? And now we have to start with this leaky ReLU. And in the ReLU, we have seen that for the negative values, it is always zero. And now this leaky ReLU is for the modification of that negative portion. So this is that previous picture that you have on the previous slides, which means that for negative values, it is zero. Now, what we are going to do in this ReLU, that we are introducing a, which we will multiply with the values here. And, and the value of this a would be 0.01. And when you will do this, then your line of the curve would be like this. And it will go like that up to minus infinity. Yeah. And it is going up to here up to positive infinity. So here in this ReLU activation function, we handled basically that negative portion which was here, and for that we were saying that here in this activation function, this activation function is not able to map negative values properly. So now that disadvantage or that issue is now removed, and you have this thing which is going from minus infinity to plus infinity, and it is differentiable and also monotonic, because differentiable when x is changing, y is changing. So this is the definition for the differential. And for monotonic, increasing or decreasing. So that trend is also there. So it has both the properties. And this is called leaky ReLU. And now moving next to another one, which is exponential linear units, or you can shortly call it ELU's function. So this is the equation for it. When the value of x is greater than or equal to 0, then you have the x, you will have that number. Otherwise, if it is negative, then you have something like that. Again, alpha is multiplying. So if you will see here, so it is very much from 0 to onward, it is similar to that previous ReLU. But here it is just going a little down, which is, you can say, if it is y, then it is in the direction of y minus or y negative, and then it is going straight, something like that. But this value is now not zero. Huh? One thing is sure, that this value is not now not zero, and the median or the mean of this curve, which is this one, is close to zero, because this point is zero, and this mean is almost close to zero. So again, this activation function is again modifying that negative part of the ReLU function, and if the mean is close to zero. When the mean of some curve is close to zero, what it means actually? Mean means the average of all the values. Then the meaning would be this, that the average values is this, then it will mean that the model will learn faster, and also it will converge on some point speedily. So that's why this convergence and the faster learning is mentioned here. And it is differentiable, because now again, if I will clear this drawing, this portion, or you can say from this point to onward, it is very clear that it is differentiable, because x is changing, y is changing, x is changing, y is changing. But this is something, again, it is in a decremented state, but it is again not, it is something going some negative value constant, huh? Like zero, huh? Like zero that you have in ReLU. So that's why this portion is prominent. So here, but it doesn't mean that it is not monotonic. It is monotonic. Okay, because increasing trend is there. And what is the definition for monotonic? Increasing or decreasing, huh? So increasing trend is there, but the more prominent is differentiable. So that's why differentiable is written there. But if you will write monotonic also with it, it's correct. It's not wrong. Okay, it's correct.
But maybe it's not negative anymore.
Say again. Yeah, you can say, because this is something, it's not negatively monotonic perfect, because this portion is unclear, okay? For the definition of monotonicity, it is unclear, but this is something clear, but the sentence that you have is perfect. Okay, moving next. These are the different activation functions. uh, Identity, sigmoid, tangent, arctane, ReLU, Riki, randomized, parameter, binary. So, and their curves are also displayed here. And by looking on these curves, you can identify that it is differential or not or whatever. But but here it is tried to present all of the active nonlinear activation function which are available. I tried, but it is not necessary that you have all these. And one information is that for the tangent h and the sigmoid activation function, this is an information that you cannot use it in real time models. If, for example, the results that you want very quick real time, then you don't have to use this tangent and sigmoid in those models. Why? Due to this problem. And what is that problem? Vanishing gradient problem. This problem is the meaning from each gradient. If you will look on some diagram which I presented somewhere in the logistic regression, this one, okay, this is the gradient for one point, and then and this is again the derivative for another point, another point, another point, another point. This here, you try to reduce this cost, or you try to reduce this gradient, you can say. When you will try to reduce this gradient, and if the value of the weights are becoming zero, okay, then this is called vanishing gradient problem. This is called what? Vanishing gradient problem. That the values that will decide about the optimization of your weights, they are becoming zero, and it will make all the things mostly zero. Okay, there is a discussion. I will do that, inshallah, when the point will come. But up to that point, this is enough. And
It will stay at the point, the same position, all right? On the vanish.
no, that means that the weights that you are trying to optimize, the cost function that you are trying to optimize, and in that cost function, the weight will be very much close to zero. Those would be very small values. And when you are multiplying again and again, it will become small again. So those values would be almost zero, and it will give you zero result, zero values. Okay, it will, yeah, it will disinfect the accuracy of your model. Okay.
Do nothing.
Hmm?
Do nothing.
We will do something, but if this situation will happen, then you cannot do anything. So that's why it is instruction that do not use tangent h and sigmoid activation functions if you want something results like real time from your models. This is just an instruction. Okay. And for vanishing gradient problems, okay, we can do something. That's why you are using, for example, you are using gradient descent, stochastic gradient descents. These algorithms will do something for you. Okay, this is what we discussed in logistic regression. That's why I discussed those four components in detail. I will not discuss those again in detail. And those discussion, we will use them in also in the discussion of neural network, because the mathematics of neural network and logistic regression is same, except some structural differences. So now Now we are on we are basically already started the topic of neural network, and we said that in neural network we will use the softmax. We will use the softmax. In the despite of this sigmoid, okay, we said this in the beginning of the neural network that here we will use softmax. Why we will use the softmax? Multi classification.
Yes.
For multi classification, so it means that we can also use sigmoid if we want. Okay, so if we want to do the binary classification, you can use sigmoid. Okay, so anyhow, so we already did this discussion in the beginning, and now the question is how the neural network will learn. But to answer this question, first we have to go through these two terms. What is feed forward and what is back propagation? And only then we can understand this, how neural network will learn. Because in the training phase, when the neural network will optimize its weights, it will go back and forth, back and forth, back and forth, okay, during training. So for that, you have to understand what is feed forward network. That feed forward network will also give you the definition for the feed forward neural network. And the other one is back propagation network. So feed forward, from its name, it's clear that you only have to move in the forward direction. You only have to move. This is the short definition, okay? You only have to move in the forward direction. In the forward direction. You only have to move in the forward direction. What is the meaning of that? From the model, whatever the output you are expecting, that output you will get from the input. From that output you will get from the input, and there is no need to go back, or there is no need to restart the algorithm that is with some other value. That is called fine tuning. So anyhow, again, in feed forward network, you are going always in the forward direction. Like here, the picture is given, sorry. You are going from here, from this input layer, you are going in the forward direction. This is green one is the hidden layer, and you are getting your output. This is the direction of the feed forward. And then you will not go back, okay? You will not go back for updating the weights. And why we normally update weights? To get more accurate results. To get more accurate results. So, and how we normally define that our results are not accurate? By finding the difference between the predicted result and the actual class which is available in the data set. We take the subtraction, and then in this way you will normally find the difference. If, for example, difference is zero, if difference is zero, it means you don't have any loss, It means you don't have any loss. And then your neural network will not go back. It is only in the forward direction. And if in your model you have this kind of thing, that it is always moving in the forward direction, and you are getting your expected output there, this is called feed forward neural network. Okay, this is called feed forward neural network. Because in this network, you don't have to go back for finding the correct answer or for finding the optimized weights, and you don't need any fine tuning. What is fine tuning, by the way?
Just the one.
Just the way it is.
For example, if I take
For
the general
specific use case.
model, and I will fine tune it to my case.
Yeah, normally, if, for example, you have the model, and that model is already trained on some data set. Now you have your own data set. And when you will train that data set again on your data set, that is something fine tuning, okay? You will tune also, you can play with the learning rate or whatever, but leave it. We are in the beginning. I don't want to go into that deep detail, okay? But normally this is the fine tuning. And back propagation. Now come to the second point, back propagation network, BPN. So now your model maybe feed forward or whatever the model is, neural network, it is neural network, and it is now executed and you got the output, that output is your, that output that you got is not the output that you were expecting. Which means there is a difference between the predicted and the actual class. So this is not the output that you were expecting. So then what? You have to improve this result. You have to improve this result. And how you can improve that? Then you have to go back. Then you have to go back up to that point where you have the weights for your inputs. And if your weights here in the beginning, you have to go again up to that point. You have to take the difference and then you have to modify the weights, and then you have to go with the updated weights again in the forward direction. So this is when you normally go back to update the weights, that is called back propagation. You already have seen this in the previous courses that you have learned. So I am moving next. This discussion is again mentioned here. So you have the graph. This is the xi is the input, yi is the class which is available in the data set, y cap is the class that is predicted by your model, and this is the point for the actual class, this is the point for your predicted class. And you have to do what? If there is a difference, you have to find the difference by doing this subtraction, actual minus predicted or something like that. If your difference is 0, then you don't have to worry, everything is okay, accuracy is okay, and go on. And if this difference, if you have the difference between these two values, then you have to calculate this difference. And from the topic of logistic regression, we know that how we can calculate this difference through cost function or through loss function. And what was our objective at that point? To reduce the cost, to reduce the loss. This was our objective. So now how we can do this? How we can do this reduction? We can do this reduction if we will use the BPN, back propagation network. Okay. If we will use the back propagation mechanism that we saw in the previous, then we can go for the reduction of the loss. But we have to care that we don't have to make our value 0. Okay. This is what I said earlier. We don't have to make our value 0. It should be close to 0, but not 0. Okay. Now we are still in the same topic, how the neural network will learn. And now for the training, for the reduction, we will have some equation for finding the cost function, and then we will use the algorithm gradient descent. Gradient descent. This is gradient descent. This is what we use in the logistic regression. I said the mathematics of neural network is the same as the mathematics of logistic regression, but minor structural differences. In the logistic regression, we said this strictly that we will use sigmoid because that was for binary. Even you can use it for multi, but for changing something in it. Anyhow, for gradient descent. So at that point, we studied gradient descent there in the logistic regression. And we also studied stochastic gradient descent that is coming next. And what is the gradient descent? That picture I repeated here. And this is this point, and if you are calculating derivative, that is called gradient. And then you will reducing, you are moving to another point, and then you are calculating derivative, and this way you will reach on this local minimum. This is the drawback of the gradient descent algorithm. Okay, like hill climbing. If you will memorize artificial intelligence or whatever, hill climbing is the drawback in that algorithm is it is giving you the local minimum or local maximum, not the global minimum or not global maximum. Similarly, gradient descent algorithm will give you what? Local minimum or local maximum. I said local maximum if you are using some other algorithm. Okay. So, but for this case, it will give you local minimum. I will discuss it later on. But here, the difference, how the neural network will learn. So we can, in neural network, we can use this gradient descent. And this will do what? it will find the least cost. It will find the reduced cost. But there is an issue with the gradient descent, and that issue I already told you, huh? So that it will give you the local minimum. Then what is the solution? We will discuss it in the next slide. Anyhow, so okay, we can use this gradient descent in neural network, because through this gradient descent we can reduce the cost, or we can reduce the loss. But there is another problem, that if we have many independent variables, huh? Independent variable means inputs, your inputs, huh? And dependent variable means the output. The easy way to understand, huh? The easy way. So if you have many independent variables in your data set, many means if the number of the independent variables or features is more than the ideal limit that is good for your model to give better accuracy, yeah? So if the number of independent variables are more than the ideal limit, then what will happen? Then you will have the scene of curse of dimensionality. Then you will face the curse of dimensionality, which means the size of the data set is yeah, huge, especially in number of features, And when you will have more number of features as compared to the ideal limit, then the accuracy of your model will be disturbed. Okay, you will not get good results from your model. But sometimes if your number of features are limited or less, then you have to add features into it. Okay, up to that ideal limit. You have to add features, and when you will add this feature, then the accuracy will increase. So both dynamics are there, but the your boundary is ideal limit. Oh, anyhow, so then how we can solve this curse of, how we can get rid of this curse of dimensionality? Then the solution is again gradient descent. Okay, that will find the least cost for you. Now, moving next, and you have studied how you can reduce the features, how you can prepare the data set in the CLO1, how you can reduce the number of features. Okay, now we are still in the same topic, how neural network will learn. And now we will see the difference between the gradient descent and the SGD. I told you that the gradient descent is like a hill climbing. It will give you the local minimum. For example, if you are, this is your prediction and this is the cost for it. And if you are moving from here, this is your gradient, you can come here or you can come from here to here. So this is the deepest point now. Now this is the deepest point up to this point if you will use the gradient descent. It will not give you this deepest point, which is actually the most deepest point, which is the global minimum, huh? But this gradient descent will not give you this result. It will give you this result if your point is here. If your point is here, okay, then it will give you that result, okay? Anyhow, so this is gradient descent. But if you will use the stochastic gradient descent, then this situation will not happen. It will give you this deepest point, even it is starting from here, okay? So that is the major difference between the gradient and the stochastic gradient. And the other difference is, you can see from this, these pictures, this difference is with respect to data set. That this picture here, you can say this is the data set and you have the number of rows in that data set. And if you are using GD, then the GD will consider all these rows. And then what it will do, just remember the logistic regression. It is considering one row plus, and then it is calculating cost plus second plus third plus fourth, and then dividing by total. That it is calculating average, if you remember, because we use gradient descent there, huh? So here it will calculate average. But the thing is that gradient descent will consider all the rows at once, and then it will, yeah, give all that data. It will plug this all data into the network, and then output will be created, and with respect to actual value, the difference will be calculated. And here, if you are using gradient descent, it will calculate what? It will calculate average cost of all the inputs, And how it will calculate? It will do the back propagation again. If you will use this gradient descent in neural network, okay? It will do the back propagation and it will adjust the weights until you have your minimum value in the variable or for your loss. For stochastic gradient descent, it will do the same steps again, but it will consider the data in your data set row by row. It will update the weights row by row. It will not take average. It will not take average. That is the difference between the GD and the SGD. Okay. Now, we are still in the same topic, how neural network learn, and now we are going to say something about propagation. We already know that what is back propagation, moving in the backward direction, and updating the value of the weights. That is what the back propagation is. Otherwise, if you will say that within the neural network, if we will move from output layer 2 towards backward direction, then this is called back propagation. Perfect. And why we normally go in that direction? To update the values of the weights. And why we need to update that? Because we have a difference between the expected outcome and the actual outcome. And that difference is called the loss or the cost, and we want to minimize it. So that's why we are now going to do the back propagation, and you will keep on doing this back propagation until you have your minimized answer or minimized error in your model. This is the picture. You already know, if you are going in a forward direction, this is the direction. If backward direction, then this is the direction. And here the weight layer, the layer with the weights is also mentioned, which is the part of the hidden layer. Okay. So you will come back up to here, up to this point. You will come back and you will do what in backward direction? You will use some formula. For example, mean squared error formula. You can use it, and you will calculate the difference between the predicted and the actual by predicted minus actual something, and you will multiply, or you will use, if it is MSE, mean squared error, then you will multiply it with 2. Or if there is some other formula, okay, the things for those formulas are also available. You have to do that. And then you will have your updated weights. And then you will start with these weights again, and you will come here. With that mean square error, which is a formula, you will calculate the error. I will explain it. When I will go into the last portion of the source code, I will explain it, okay? What in the backward direction, what actually you do. Actually, you know only that you will move into the backward direction, but what are the steps you will do in forward direction and also in the backward direction? We will see that. But generally we can say that when we will move in the backward direction, we will update the weights. How? Just hold on. We will reach there, huh? Oh, by the way, source code is there. This first page, second, and then here. I am now explaining this output first to you, what this output is, and then you will understand what this program is. Here, this output is saying prediction result is this, and it is giving you some value. This line of the output means that in the source code, we are giving a feature, which is a vector. We are giving a feature, and then we are giving its class, either class 1 or 0. What is its class? We are also giving. And we are giving also biasness. So what we are giving? We are giving x1, we are giving weight 1, and we are giving biasness. So these things here, if you will see, okay, these are the libraries. And here, this is the vector, input vector. We are giving this vector, which is containing 2 values in a list. And this is what we have. Another thing, I am calling it weight. Here it is 2 It is to here. Now see it again. So this is the vector. We are passing into it with these two values, and this is the weight vector. You can say two values, and here the bias variable which has the value 0. So this is something we are giving into our model, and our model is predicting some value for it. How it is predicting? First, it is this is the sigmoid function, and you know what is sigmoid, huh? It is 1 over 1 plus e raised power z something minus something like that. It is written here some, and it is the another function make prediction. What is this function? Is taking input vector, weights, this is input, this is weight, and the bias. And what it is doing? It is doing multiplication first. In logistic regression, in neural network, if it is same, then you have to multiply inputs with the vector. This is here we are multiplying, dot multiplication. This function dot will do that multiplication automatically for you. It is available in Python. And then we are adding bias into it, and we are getting information in layer 1. This is a variable. And then we are applying sigmoid over this layer 1. And we are getting some value which we are storing in a variable layer 2, which we are returning here from. And then in the next, if you will see, we are calling this function make prediction. We are putting this input and weight into it and passing the bias into it. This function will be called, which is calling this sigmoid further. And it will calculate some value, and it will store it in this variable prediction, which you are printing here. The prediction result is prediction. The prediction result is prediction. This is what you are seeing here. Prediction result is 0.79. Prediction result is 0.79. This is what you are seeing here. This is prediction result is 0.79. So here you have given one input vector, one weight vector, and the biasness, and you have seen, and your model is predicted that the value for it is 0.79, which is greater than 0.5, which means the class is 1. And if it is less than 0.5, which means the class is 0. Okay, the class is 0. But this value is giving us the hint that the class is now, for this input, the class is 1. Okay, and now the other line, prediction result is 0.87. Okay, let's see this in the source code. So here, changing the inputs. Now we are giving another vector, which is this one, 2, 1.5. And then we are calling this make prediction. So now we are checking this function make prediction with some other input vector. The weight vector is same, but input vector is changed here. Input vector is changed here. So input vector, weights, bias, we are passing into it, and it will calculate the multiplication sigmoid, and it will return the result into this variable prediction, which we are printing. The prediction result is prediction. And for this second line, 0.87, this is the output for that. That we have changed the vector, and the class which is predicted by the model for that input vector is 87. 87, which again means, what is the class? 1. But actually it is wrong. Actually it is wrong. And now we want to, and why now we want to calculate the difference. Okay, so here the prediction that we got here is 87, which is repeated here, and then the error is what? Error for this second vector is 0.7, which is, you can say, 75%. 75% error. So we know our data, so that's why I said that this second result is wrong, and the error percentage is 0.75. And if you will look at how I can check, I will calculate the derivative, and then derivative, subtraction, something only that way. And how I can do that? Look over here. Now I am saying target is 0, which means class is 0. And here I am using np dot square, which is, and prediction minus target. Prediction is that variable, target is that variable. Prediction is prediction by the model. Target is your actual class. So you are taking the subtraction and then you are applying this square function which is available in this numpy. And this square is what? Your mean squared error. Okay, this is the formula for the mean squared error. It will calculate that error. Okay, it will calculate that error and then prediction, error. So that line that you have seen in the output, prediction is equal to this and error is equal to this. This is giving you that answer. Prediction is equal to this and error is equal to 0.75. That formula is giving you that idea that you have this percentage of error or this value of error that you have here. Now, how we can correct it or how we can do that? So then we have to find the derivative for one point and then for another point, and for another, you can calculate only by going back. Okay. Going anyhow, but for one point, how we can calculate the derivative? Let's see that. So we were here. Where were we? Okay. Here, derivative, huh? Prediction minus target, which is the difference, and you are multiplying it with 2, and you are getting this derivative with a simple formula. You can have different formulas for that. And then you are displaying derivative is derivative, and you will get the value for the derivative for that first point, huh? And which you are seeing here. The derivative for this 87 that you are getting and this error, the derivative is 1.74. So the value is 1.74. For this class 0, it should be close to 0, but not 0. Then it is correct. Okay. Now, again, this value, which is 1.74, it should be close to 0. Then it means that the difference is almost 0. Okay. But not 0. This is what we said in the previous slide, that it should not be 0 because then you have vanishing gradient problem. Okay. So our this value should be close to 0, maybe 0.01 or 0.3 or 0.0 something, huh? But this 1.75 is giving us an hint to reduce it close to 0. And if you will have the negative value minus 1.70, then you have to increase it close to 0. Okay. Then you have to increase it close to 0. But this is a positive value, so that's why you have to reduce it and close to 0. But if it is a negative value, then you have to again move it close to 0. So then you can say that you have to increase it, huh? Anyhow, so this is how you are calculating derivative. Okay, derivative is done. Now, how I can update the weights? Just one step behind, huh? Here, weights 1, which is this one, minus derivative, you have the value updated here in weight 1. And then we are calling the make prediction again. We are calling this make prediction function again with the input vector and the weight 1 with that updated weight, huh? Here we are passing updated weight, not that previous weight, updated weight and the biasness, and you will get the prediction. And then prediction minus target and this star 2, this is what? This is equivalent to power, I think. Power something. So you are calculating power, and whatever the result is that you have air. Now you are again calculating the error percentage that you already calculated, huh? And then now printing prediction from the prediction variable and error from the error variable. And here you are seeing that your now prediction is, before that it was 87 value, and now you have value what? 0.014. But this value is giving you an idea. Which class? 0. Okay. And now this error is what? 0.002 or 23 or 88. It is close to 0, but not 0, huh? So now this value is giving you a hint that now it's okay. Now the weights are okay. Previously it was not okay. And here in the source code, this is up to this point all individual steps are written for easy understanding, okay? And up to next, it is written generally, not each step. All the steps are copied again here. For example, sigmoid is written here. You can see the sigmoid again. Now all these steps are written into the form of a class and functions, and functions. And in this way, otherwise the steps are same. But here we don't have the training phase. You are performing one step by own. Now for training, you have to go back and forth many times, So that training phase module is not here, which you will see here. Here you can see the training, So you are doing the same things again and again. And now this module is available here, which will make your model able to go back and forth again and again to update the values of the weights. And here we are giving the input to the vector, the data set, you can say, okay? Input to the, so here you have multiple vectors, 1, 2, 3, you can raise it, and 4, 5, 6, 7, 8. So you have multiple vectors. And the first vector is, it has the class 0. Second vector has the class 1. Third vector has the class 0, and so on. This is what it means. And then you are calling with the learning rate, and you are calling your neural network, etc., etc. And then you are seeing this chart for the neural network, for the whole data set that you had given here. What it means, so we have set in that model, we have set 100 iterations, we have set, or maybe I think 1000 or 10,000, but in the chart it is displayed, it means 1000, then 10 to 20, 30, 40, and then it will become 10,000 here, because it is scaling, but in the code we have done, I think we set 10,000 iterations. Let's see that. So, but this is the scale, and you can understand that this is equal to 1,000, and this is okay 2 and 4, 5, and something up to 10,000. And here you have the error for all the training instances. What is the error? This is the error value or error. When you were on the 0th iteration of your model, your error was at the highest position. And when you are increasing the number, when you are done with the number of iterations of your neural network, for example, here, when the 10 iterations were finished, your percentage would be maybe here. And in this way, you are seeing that up to 100, this is the last error percentage or value which is existing in your model. This is the error percentage. It can be maybe, I don't think it is maybe equal to something like that, but not that maximum point. So that source code is running over 10,000 times or whatever, and it is giving you, finally, it is calculating this chart from here. And I copied this text from here, from this, the source code from here. If somebody want to understand, maybe I'm not that successful to give you the understanding of the neural network, but if somebody want to understand how neural networks will work in each and every step, from the smaller step up to the higher step, he can go on to this page and he can read and implement the neural network from the scratch up to the last point. This is a very good page for your better understanding, okay? Okay, now moving next. So we are finished with this logistic regression. We are finished with this neural network. Fundamental concepts of neural networks, okay? CNN is remaining, that we will cover in the next CLO, because CNN is a deep learning model. I don't have to go with that, but I will go, okay? I will go with that. In this course, it is not compulsory on me to give you the understanding of CNN, but I will go with that. because neural network, you can use it as a supervised learning, you can use it unsupervised, you can use it reinforcement. So I have neural network here now, it is done, and we will touch it again with the CNN in the unsupervised, with the unsupervised approach. And now we are moving toward the decision tree, and then this CLO will be finished, but it will take time. Let's see. Decision tree, you already know. What is decision tree? So, like trees that you have, the trees that you have seen in the different courses, huh? That is the same definition. So, but here in machine learning, decision tree, like other supervised learning algorithms, decision tree will handle regression and classification. It can have the ability to handle regression and classification separately. It can handle regression, it can handle classification. So you can use the decision tree for any of these. And how you will do that? You will start from the root node. Okay, you will start from the root node, and then you will put maybe your some attribute there, and then you will split it into further subtrees, huh? Subtrees, and you will keep on splitting that into further branches until you reach at the leaf node. That is the normal definition that you have already seen for the tree in any course, either data structure or algorithm or whatever. So that is the same. Now, what are the types of the decision trees in the machine learning? So there are two types, categorical and continuous. Categorical will do what? It will handle only those features which will have something, you can call it category. For example, if you have a column, and if that column has values either this or that, like for example, either email is spam or not spam, two possible. That is called category. That is called classification. Category, classification, division, the same name. So categorical variable decision tree. So this is a decision tree which can fit into one category or the other, either this class or that class. If you have the data like that in any feature, if you have the data like that, either this or that, then the decision tree that you will make based on the based on that data would be called categorical variable decision tree. That variable means feature. The examples are given here, that the coin can heads or tails, two classes. Animal can be reptile or mammal, two classes. Continuous, we already know the definition of continuous variable decision tree. That decision tree will handle continuous data. Okay, shortly, without going into detail, that decision tree will handle continuous data. And what is continuous data? Previously, we saw the example of house pricing. House pricing with respect to parameter, number of rooms, number of bedrooms, or whatever. And also you can say the real numbers. If you don't know, okay, you can say real number. Real numbers is continuous. 1, 1.5, 2, 2.5, something. And in between, you have the values. I can say much more about this, but we already know what is categorical, what is continuous. So that's why I am moving forward. So we can use the decision trees for the regression. So that's why, that is the reason that continuous decision trees is one name, or regression decision trees is another name. And here you will handle what? Continuous type of data. Okay, moving next. These are the two categories. Here, the example for the categorical variable decision tree. And the example is, draw a decision tree to predict whether or not a person is fit based on what? Age, food, and exercise. These are some extra information. Based on this information, conclude that the person is fit or not. Okay, the question is person fit? Age is less than 30? If yes, Then you have another question, eats lots of pizzas? If yes, you can say unfit, huh? And if it is no, then we are saying fit. Similarly, age is okay, greater than 50 or less than 50 means when it is no, you are coming here when it is greater. Doing exercise, if yes, fit, no, unfit. So this is simple example for categories. Now after each decision node, this is called decision node, huh? After each decision node, you have two classes, huh? Two categories or two classes. What is continuous? Now example is, what is the salary for the players who have more than 6.5 years in the league, the players who played these leagues, huh? But less than 118 hits. So what is the salary of the players who have more than 6.5 years in the league, but less than 118 hits? And similarly, another question is, what percentage of the data set fall in this category? So initially, okay, you can see here, this is, you will keep the whole data set at the root node, okay? The whole data set. This is giving you the information. This is the 100% of the data set. This tree sometime has maybe missing information or whatever. But suppose that this is 536 is what? This is the total number of players. So suppose this is not the salary, okay? This is not the salary. But in the next node, it is salary. But suppose here you have the total number of players. And then what? Here's we have a condition, years. We made this, here this tree is, we can make it short, okay? But here, due to this condition, we are making it a little bit lengthier. Anyhow, as it is a copy paste, so okay, go on with that. Years less than 4.5. This is not a mistake, okay? This is not a mistake here, okay? This 6.5 is handled here. So if, and here we are checking that years less than 4.5. If years are less, if condition is true, then we are moving here and we are saying maybe 226 number of implies here, and it is what? 34% of this whole data set. And if the number of years is greater than 4.5, when it will become no, then here you will have 66%. And this is not the number of employees. This is the salary, okay? This is the salary here, because the numbers are not equal, because the number is not matching here, okay? And I don't want to edit it, okay? So I don't want to edit it because here we are getting the idea. What is continuous? So but one thing is sure, that it is 66% of this when you have, if the number of years are more. Okay, then come here. If the hits are greater than or equal to 42, if the number of hits are greater than 42, then the players with hits greater than 42 is 30% of this, is 31% of this previous thing. And you can say, now it is the salary maybe. Suppose it is 204 is the salary, but I think maybe from this 226, it is still not salary. It may be the number of players. And then again, here we are checking if years less than 3.5. If still years are less, hits are greater than 42, but years are less. What we are going to say, okay, whatever the hits you have, if your experience is low, your salary is low, okay? This is here what we are going to say, if whatever the number of hits, but hits, here we talked about hits here. But here we are talking about hits up to this point, and we are saying whatever the number of hits you have, if your experience is less than 3.5 years, your salary is this 1.142 Saudi riyals or your dollars, huh? And 20, this is 21% of that previous stage, Similarly here, if the number of years are greater, then your salary is greater, greater than this one, and it is 10% of this previous step. And if your hits are larger, then here the salary is increased, and it is 3% of this previous one. So similarly here, when your number of years are greater than this 65, so here the experience is greater than 6.5 years. And what is the salary of the players? It is written here. What is the salary of the players who have more than 6.5 years? This branch is handling all that scenarios. And if it is less than 118 hits, here we are checking. Hits less than 118, this branch. And if hits greater than, then this sub branch. And here, if hits are less than, it is 34% of that previous, and the salary is 465. You can call it salary, or you can call it the number of person. Sometime it is more better to say it number of persons. Here, for example, at the root node, it is number of persons. For sure, it is number of persons. How we can say that this is the salary of 100%? We have to find the salary. And here, and then here, 34% to 226. Okay, if you can find the percentage of this 226 with respect to this 536, and if it is 34%, you can say it is number of players. It is number of players. Otherwise, you can check it. I checked somehow in the past. I checked it already. So anyhow, so if the number of years is less than 65, you have this, this, and this, and that. What this tree is giving you idea that your conditions are not fixed. Your conditions are not fixed. It is changing. It is. Sometime you have 3 branches, 3 leaf nodes, and some here you have 2, sometime 2, sometime 3, sometime 4. It can vary, So the data, the nature of the data is continuous here. And if you have the data of the nature of the data is continuous, you still can build a decision tree for that. But you have to do one thing, which is mentioned next, but I can mention it now. You have to make the values of your features close to categories, okay? If it is not close to categories, you have to introduce some threshold or whatever, and you have to modify your values close to categories. For example, if there is some column and there are values in it, and those values are random. Some is 5, other is 50, other is 100, other is 200, other is 700, other is 1 million. So these values are very far from each other. Then you can do what? You can apply some technique over these values, and you can say, you can introduce some ranges, okay? And then you will represent all those values with some ranges. For example, range 1 to 100, or range 100 to 10,000, or 10,000 to 1 million. And now you have only 3 categories. And now you will have only 3 categories. So you have to modify your random data close towards categories if you want to draw decision trees for continuous data. You have to modify your continuous data, and then you can draw. Okay, moving next. What are the terms for the trees? We already know. This is called the root node. And here, this root node is splitted here. We normally keep our data set here up to this root node, and then we will split those data set into further branches. And then the node, this node, or this node, this orange one, these orange nodes are called decision nodes, where you are doing decision. And these green ones are called terminal nodes or leaf nodes. You already know that. And this thing can be called subtree. This can also be called subtree. Even this whole can be this left subtree or right subtree. All these terms you already know. So that's why I'm moving fast from this slide. What are the assumptions that you have to assume before going into the setup of the decision tree? So you have to assume that you have to put your training data set on the root of the decision tree. Okay, this is the first step. And then you have to prefer that your feature, your columns, they must have the categorical values in it. Hmm? When I say categorical values in it, then it means that in those features you will have something, two classes or three classes or four classes, huh? Yeah, this is what I mean actually. And if you have the continuous, then you have to modify it into close to categorical values. And the terms that we used here is, if your data is continuous, then we have to discretized prior, before, prior mean before. We have to discretize before. Discrete normally means different and unique. Okay, so if the values are random, you have to introduce some ranges or whatever, so that it will be more closed. It will look like a category, not like a continuous data. And when you have your data set or the training set at the root, then you will split into further branches, and you will keep your records recursively on each node of the tree. This is what records distributed recursively mean, that on each node of the tree, you will go from top to bottom recursively. You will get your decision recursively through this tree. And you have to place your attributes. How you can place your attributes? Attributes again means features. Starting, we can place it on the root, or we can place it on the internal nodes within the trees. But how we can use some statistical technique here. We can use some statistical measure or metric here, some equation here, to select these attributes for the root and the internal node. For the root of the decision tree, it is not difficult. You have to put the whole training data set there. But for the next steps, you can use some metrics or measures. Let's see that. Now, previously we were seeing how the neural network will learn, and here we have a question: how do the decision trees work? How this decision trees work? Initially, when you have your data set on the root node, then the first step that you have to do is you have to find the features that will have maximum information in it. When I say maximum information about the target class, or the class that you want to predict. From the model, you want to predict something. From the model, you want to predict something that is called target feature. That is called target feature. And now, when you are at the root, you will try to find those features from the data which have the maximum information about that target feature. About that, you will find that feature. You will not find that feature manually. Okay, you have some techniques for that available in machine learning that you can use. And then after finding that feature, then you will split the root node or the data set. Root node means data set. Then you will split the data set into further smaller groups. And you have to take care for the further smaller groups. What is the instruction for the further smaller groups? You have to take care that these groups, the data in these groups, must be pure. What is the meaning of this pure? That they will have the categories, that they will have, again, the categories. You will not have random data in it. It will have, for example, here the example is given here, by or not by, two categories. When you have, in general words, you will say the data must be similar, not too much diverse. Okay, these are the general words you can use. So the data should not be diverse, but these are not the proper words. Or in other words, you can say you don't have too many classes or something like that. Anyhow, What are the algorithms that we will use for the decision trees? Some are mentioned. ID3, we will use this, which is extension of D3. We will use this algorithm C4.5, which is successor of ID3, which is the extension of this one, the next version of ID3. We will use the CART, which is what? Classification and regression tree. These blue ones we will study in this course. But these CHI-DE and Mars, which is chi-square and multivariate, we will not study this. You can read it by yourself, okay? Because I cannot cover all these things. But I am still sure that you have not studied this CART before. Maybe you have studied this ID3 or C.4, but I'm sure that you have not studied this CART before in your machine learning. Have you studied? Have you studied? Maybe, maybe you have not studied this ID3 also, huh? So this course of machine learning is, the title is same, but content is not same, okay? Okay. The title is same. I'm sure that but the content, inshallah, that would not be the same. Starting would be the same, but then you will see something. So we will see anyhow these three algorithms only in the decision trees, and then this decision tree will complete. Otherwise, it is not complete. We are not only want to get the definition of the decision tree. No, I don't want. We don't want. So now moving next, this is the general approach of the general algorithm for the decision tree. This is the general algorithm, how the decision tree will work, written theoretically, not mathematically. Written theoretically in sentences, not mathematically. What we will do in step 1, we will introduce a root node. And on the root node, we will keep the whole data set, our training set, on this node. And then step number 2, we will find the best attribute. We will find the best feature which is available in the data set. We will find that. How we can find? We can find through some attribute selection measures. This topic will come next. You cannot find the best attribute manually, okay? No. You have to use some measure which is available in machine learning, which is available in Python. You only have to use it and you have to give your input into it. It will do the work for you. So we can select the best attribute by using some attribute selection measure. It will come next. And then but the step is what? We have to find the best attribute. When the best attribute you have in your hand, now the next step is splitting. Next step is splitting. Divide the S, that root node, into subsets. Divide the root node into subsets, into further branches, with the possible values for the best attributes. You have this measure, attribute selection measure, which you will use each time. After the splitting, you will use each time on each node, you will use this measure to calculate again that which feature is the best from the remaining. So step number 4, generate the decision tree node. What is decision tree or node? This is decision node. You already know. We already know. This is easy. This is easy. These are the leaf nodes, and the nodes between the leaf nodes and the root node are the decision nodes. Okay. So generate now. So in the previous step, when you are splitting, okay, then what? That split, okay, go again. Create a decision node and then again split. Generate a decision tree node. Okay, generate that. And you can generate it again. This decision tree will contain the best feature. The feature with the maximum information, that is called best feature. This would be the step 4. Okay, now decision node. And now when you have the decision nodes, what you can do? Recursively make a new decision tree. How I can make? Just repeat from step 3 to up to step 5 or step whatever 4 again. Now this is recursion. You are going recursively up to the leaf node. You will go like that until you reach at the leaf node. This is theoretical algorithm of the decision tree written in sentences. But, and here we have seen how we can select something, how we can select some node, how we can find the best attribute. This is something we need that. Rest is splitting, huh? Only one thing we need, that is what? Attribute selection measure. How we will select the best feature. The rest is just steps, huh? You are not doing anything, but this is something you need that. And here, previously we said that we will consider ID3, we will study these three algorithms, which is the main algorithm showing the working of the decision tree. And now we are starting with that ID3 algorithm. This is the top down because it is, you can apply it on tree, so top down, from root to leaf nodes with no backtracking. Backtracking is not. If failure occur, you cannot backtrack. Okay. If failure will occur, you cannot backtrack. Anyhow, but let's see ID3 algorithm. Again, you will start with the S, the root node, huh? And then step 2, on each iteration, you will calculate the entropy and the information gain. Now this is a new thing. These are those measures which will select your best feature. These are those. So on each iteration, you will calculate entropy and the information gain. For what? For unused feature or attribute of the data set, of the training set or whatever. In the training set, you have features. And the features that you have not used yet, you will select them one by one randomly, okay? And then you will calculate entropy and the information gain. You will select some feature, you will calculate entropy, information, and information gain. I will say shortly, okay? Entropy is okay, but information gain, I will say shortly, IG, okay? So some people can express entropy with H. Some people are also expressing entropy with E, yeah, with the variable. So you can calculate this H and IG for each unused feature of the data set. And then you will have these values. And by looking over these values, then you can say which is best, which is not. But after comparison, you can understand that which is best and which is not. Step number 3, the attribute. When you will calculate these values, then the attribute or the feature with the smallest E, smallest entropy, and the largest IG, largest value, maximum value of the IG, that attribute would be the best attribute. You have to select that. You have to select that, and that will be selected. And then you will select that. Okay, that is selected. And now the next step is splitting, huh? So now you are going to split that S into divisions. Whatever the divisions are, you have to split that into those divisions. And then in step 5, you will continue to recur. This is recurrence, huh? So this algorithm will continue to recur, or you can say reoccur, huh? So it will continue to recur on each subset, on each split that you are getting after splitting. You will continue this algorithm on each split or on each subset, but you will consider only those features which are not used before. If something feature you already calculated, you don't have to do that. Okay, this is the only thing. Algorithm is simple. Let's see how it will work. And now we are changing our title to attribute selection measures. This is what we said in the general algorithm. This is what we said. You have seen the algorithm of the ID3, but here you have not seen how to calculate entropy and information gain. Rest of the algorithm is simple, but this thing, entropy and IG, is something you have to consider. Anyhow, attribute selection measure. You can select measures randomly, but this is not a good choice because it will do what? It will make the accuracy of your model worse, huh? So then you don't have the choice to select something randomly. So then what is the choice? you have to again select the best feature. You have to select what you have to identify and select the best attribute or feature from the data set. And that data set is available on the root node of the tree. And for this selection, what are the different measures which are available, which you can use? These are the different measures which are available: entropy, information gain, Gini index, gain ratio, reduction in variance, chi-square. And we will consider only the first four, not the last two. Last two, you can read it by yourself. Okay. This doesn't mean that you does not have to read it. You have to read it, but read it yourself. Increase your knowledge by yourself. Okay. I will go with these ones: entropy, information gain, Gini index, and gain. And these are the different measures which you can use to select the best attribute. To select the best attribute, because selection of the best attribute is the only point. Rest of the things are just steps. Okay. This selection of measures normally depends on what? It depends on the problems or the data set. This is just a theory. This is just a additive theory that you must have to know if you are going to select some measure, something like that. You must have to be the knowledge of that. And these measures, all these measures that you have seen here, these measures will do what? It will calculate some value for the features, and then it will sort those features according to those values. For those values, it can be from high to low. If you are considering information gain, IG, then you normally consider largest value. So then you can if you will apply on the features, it will keep the highest valued feature first, and then in a decreasing order. And if you are going to use IG, then you have to take care that your attribute must be categorical. Okay. You will assume it and you will go for the IG. It must be categorical. You will have the categories in the values of the features. And if you are going to use the Gini index, then your attributes, what? It should be in the continuous form. And when I say continuous form, now you are understanding what it means, because you know what is categorical and continuous. Continuous means real type data. We already explained. Now we are going to start with the entropy, how we can calculate the entropy. First, we have the definition of the entropy here. What is entropy? We will use this entropy to measure the impurity of an attribute. Or you can say we will use this entropy to measure the purity of the attribute. And what is the meaning of impurity or purity? That the data in the feature is categorical or continuous. Okay. If it is categorical, it will give you good value. If it is not, if your data is random and scattered, random and scattered, if it is not categorical, and maybe uncountable classes, then it will give you some worse value, this formula. So our goal, if we are going to use entropy, then in decision trees, if we are going to use entropy in the decision trees, then our goal always is to lower the value of the entropy, decrease the value of the entropy. This is always our goal. We want a feature with the highest IG but lowest entropy value. Okay. But with the smallest entropy value. So, for example, if you will see these pictures, and here, okay, the blues are 3, the red are something 7. So, if you are supposing that this red is not the categorical data, okay, not the categorical data, suppose this is something random data, then here the data set is impure, very impure, because the number of reds are more. And what is the reds? Random data. And here the number of red type of data is less as compared to the blue. Blue is something you can say accurate data, or you can say pure data, and red is impure data. And what is the meaning of the pure and the impurity? I already told you. Random, and if your data is scattered and random, it is not categorical. If your data is close to categorical, then it is something pure. It is something pure. If it is continuous, then it is not pure, huh? But you can use decision trees on continuous data. But what you have to do it, you have to modify it into categorical data that we said. And here, less impure because you have those red evidences there. And here, you don't have that red evidences. And I have already given you the meaning of this red and blue, okay? And here you don't have that red evidences, so that's why it is pure. It is not with the color, it is with the concept, okay? It is with the concept. Now, we are slowly moving towards the calculation, how we can calculate the entropy, the mathematics, huh? But inshallah, this will be easy. This will not be like logistic regression, because logistic regression was lengthy, okay? Due to that lengthy topic, sometime I can see complexities on your faces when I was lecturing, okay? So, but inshallah, here you will not, I will not see any complexity on your faces. So, so now we are supposing a data set, and that data set has n classes, n categories, huh? And then we can calculate the entropy through this equation for that data set. For that data set, we can calculate the entropy through this equation. What is this equation? E is equal to minus sigma I is equal to 1 to n, where n is what? The number of classes. And you have this formula pi log base 2 pi. Next time I will say pi log pi. I will not say the base again and again, okay? So this pi is what? This is the probability. This is the probability. Even this is also the probability, but it is the log of something. So pi is in this formula. Sorry. So in this formula, pi is what? This is something. This pi is what? It is something probability. The probability will contain some value, huh? So it is it is what? It is a probability. For what? For selecting randomly an input for class I. For example, if P1, then you are selecting a row from the data set which is related to class 1. Okay. Similarly, you are going to select another row from the data set which is for class 1. This is what PI is. And the log of the fractions, the next portions, the log, this log, when you will calculate, it will give you a negative value. So that's why we have this negative outside, which will make negative positive. It will negate the effect of the negative values, nothing else, okay? This is the simple understanding of this equation. At least we now know what these different variables are, huh? Where these different variables are. And now we are assuming that we have a data set in which we have 3 colors or 3 instances, inputs, you can say, features, you can say. So we have a data set in which we have 3 colors. What are those colors? Red, purple, and yellow. We have these 3 colors. And we have to calculate the entropy for that. How we can write this equation for these 3 colors? How we can write this equation for this data set which has these 3 colors? This is the form E. This minus is as it is. Here we have 3 classes, huh? Here n is 3. So I am writing PR log base 2 PR. This R is for red, huh? And then PP log base 2 PP. This is for the purple and this is for the yellow. We have written the equation. We have not written the detail. We don't know the detail, how we calculate it. Okay, we are going in that direction. We are going in that direction. But this is how the equation is, huh? We are moving step by step. Let's see that. So here we have some data set, some rows. Some are highlighted with green, some are highlighted with red. Red is no, green is yes. And this is another example. This is another example. Assume the y is equal to green, which means this yes is what? The green, and the no is what? Red, basically, huh? Assume. And then what? Remember this equation. This is the equation, pi log pi. Pi log pi. And here we are writing for y. Here h of d means data set. H means entropy. Entropy of the data set is what? Py log py. This y means what? This y means green. And minus. Here you have the minus, and here you have the minus. Minus Pn log base 2 Pn, and this n means red in the first figure. In the first figure, huh? In the first figure. Understood? Clear? And then how many? So now we are going to calculate the probability. How? What is the formula for the probability? If I will give you some text file, and if I will ask you calculate the probability of each word in that file, what you will do? You will calculate the total number of the words in that file, and then you will calculate the first number word. You will take the first word, you will count in the file, maybe 25. Total word is what? 1000. 25 divided by 1000, you will get the probability. Similarly, here for py log py, here how you can do that? So here y is what? Y is green. So you have two evidences here. Occurrence is 2. So 2, and the total number is what? 5. So 2 divided by 5 for the y. And log, again, this py is again 2y. Okay, write it again. Then minus, and for n is what? N is what? Red. So how many red here in the first case? 3 by 5. Log 3 by 5. Calculate it, use the calculator, whatever, and you will get this value finally for the entropy. For the entropy. Similarly, for this case, use the same formula and use 1 over 5. Here the green is 1 over 5, same formula, and you will have this value for the entropy for this data set. And for this data set, you will have this value of entropy for this data set. Now, what type of, we want highest value of entropy or the lowest value of the entropy? Lowest value. So low, we want lowest value. So from these three evidences, which one is better? Then this last one is better than this, because you have the lowest value of the entropy. Anyhow, now look over here. When the entropy of the data set is high, what is high? Maybe this one, huh? It means the data is not pure. It means the data is random, huh? Not pure. There is, you can say there is a variation between the data. But when you will say variation, people will not understand. So the exact word is random data. And further clarification is your data has many, you can say many categories, but it is not true. For understanding, I'm saying because here the examples are small, so that's why when I will say many, then you can say here you have only 2 classes and you are saying many. So the better word is random. You can see what is random data in mathematics, then you will see. If you have some circle, and if I say your data is random, then you can imagine that you will have points scattered in all that, within all that circle, huh? Anyhow, so which means not pure. And if the classes are not, and the other meaning is this, the other meaning of the high value is what? The classes are not evenly distributed. Here you have 2 classes, green and red, And you can see, okay, this is a small example, but you can see that they have the different numbers. They have the different numbers, not evenly distributed, not evenly distributed. They don't have the equal share in the distribution. And when the entropy is low, what it means? Data is pure. Data is pure and classes are evenly distributed. Here you can say we have only one class equally distributed and entropy is also 0. And here entropy is 0.72. One class has 1, other class has what? 4 numbers. So you are getting, this value is giving you clear idea. This value is giving you clear idea between the two classes that the ratio is different and how you are getting your value 0.7. This is, now you have the understanding of entropy. We are not finished yet. We have just started. Now again for 3 classes. So now assume that you have, this is your data set. Yes, no, and maybe you have 3 classes. And you are calculating the entropy for 3 classes, Y, N, and M. What is Y? Y is equal to green, N is yellow, M is red. And for Y, which is green, okay, calculated 2. 2 divided by total number. Total number is 8. 2 divided by 8, you are seeing here. And here 3 divided by 8. And similarly, this one, you are getting this value. Here I am getting value not between 0 and 1. It is something 1.56. The value of the entropy is not here in the equation. We were saying that this Pi is the probability. Yes, it is probability. But here, when you are summing them up, you are summing the values, then it is possible that you will have more than 1 for the entropy. So here, what we want to say, here the value of the entropy is 1.56. And here we are saying something that normally you will get the value of the entropy between 0 and 1. Between 0 and 1. Normally, most of the time you will get the value between 0 and 1. But this value actually depends on the number of the classes. And if you have the higher number of classes in your data set, then you will get the value higher. This is what written here. For example, if you have 2 classes in your data set, the maximum entropy that you will get, it would be 1. When you will have 4 classes, the maximum entropy you will get would be 2. For 8 classes, you will have 3. For 16 classes, you will get 4 maximum. And if you have less number of classes, you will get something in between. You can understand. But this is something shared in the literature and calculated after evidence. Yeah. So now, from this topic, now you know how to calculate the entropy. Now we are moving towards another one, which is information gain. Another measure, which is information gain. Where we use this information gain? When we want to find the best feature. Again, when we want to find the best feature, best variable from our data set, we can use this information gain. And we can also use this information gain for splitting the data. So it means that we can use it maybe after the root node also for the further nodes also. Because we can use it for splitting the data. At each internal node that is mentioned here, you can use it at any level. And it will use also the entropy. It has its own calculation, but it will use also the concept of entropy. For example, here, if you will see, this is just a line that what is decision tree. So decision tree is what? Finding an attribute with the highest IG and the smallest E. Okay. How we can construct a decision tree, how we can draw a decision tree. Then the answer for this question is that we can construct the decision tree by considering the attribute with the highest IG and the smallest entropy. If we can find these two things for each node, then we can construct the decision tree. Otherwise, not. Okay. So for example, here we have 5 greens and 5 purples, minus 5 pluses, 5 negatives. And here 5 plus and 5 negatives, equally distributed. But the information gain is low. But the information gain is what? Low. And here if you will see, the pluses are 8, negatives are 2, and here negatives are 2, pluses are 2, negative are 8. So then now you have an idea that here the number of pluses in this split, this is a split, huh? In this in this split, we have the same category more as compared to the other category. And here we have some category negative more in numbers as compared to other category. So this majority, this is something called majority, huh? So this information gain will calculate some time or maybe similarity or majority of one class, huh? Majority of one class. So we don't want our data on the branches to be many classes mixed with each other. We don't want. We want to separate the data related to the class only, related to the category only. So from this picture, at least I'm sure that you will have the idea now what information gain will do. Okay, what information gain will do from this picture, and the equation for that, and the algorithm ID3. What is that ID3? You have seen here this algorithm, and I mentioned also here ID3. This algorithm, we have seen it here. This algorithm uses what? It uses IG. It uses information gain. This algorithm will use what? Information gain. And what is the formula for information gain? Information gain is equal to entropy before minus you are adding something, but it is what? Entropy after. And you are adding some jth. I don't know, maybe children, huh? You have a node and then the children. This is the equation. Now we are going to write this equation in an easy way. What is that equation? This is the easy way. Information gain is equal to entropy of the parent minus you will calculate the average of the weights, and whatever that average will be, you will multiply with the entropy of the children. Now this is the equation which you can understand. At least you can understand what are written there. Huh? And now we will take an example and then we will calculate the information gain by using this equation. And for calculating information gain, we have to, for example, if this is the parent, we have to calculate the entropy of this parent first. And then the weights, okay, we will calculate the weights. I don't know, maybe the weight of this one or this one, we will see what it is. And the entropy of the children. Okay, children are these ones. So we will calculate the entropy of these children. Okay, we will multiply with its related weights. Okay, we will see how we can do that. And here we have an example. Consider an example where we are building a decision tree. We want to build a decision tree to predict that will predict. This is the question now, where a loan given to person would result in a write-off or not. You have some person, you have given loan to those person, and those persons have returned those loan back or not. When they returned, it is write-off. When they didn't return, then it is not write-off. Okay, this is what means up to this point. One entire population consists of 30 instances. So this is your data set, which is consisting 30 instances or people. 16 belongs to the write-off. 16 have their account clear. This class, and 14 belongs to the non-write-off class. And now, okay, as you can see here, entire population is 13 stances. And here 16 is blue, which is write off, and 14 is stars, which are not write off, huh? We have two features, further features, huh? We have two features, namely balance that can take on two values, and this balance is the name of the column. And this balance can take two values. One is what? Less than 50K. Other is what? Greater than or equal to 50K. Two types of values, huh? So, and here you can say balance. When the balance is less than 50K, this is here you are seeing this circle for it. And when balance is greater than or equal to 50K, you are seeing this circle here under this root. And then we have another feature called residence. And then residents can have these three values: own, rent, and other. Own residents or rented residents or the residence of some other person. Huh? These are the three possible values for this feature. Now the question is build the decision tree. Now the question is calculate the information gain. How you can build this decision tree? If you will know the information gain on each node. Huh? Only then you can select, okay, I'm selecting this one, and then you can split. If you will know how to calculate the entropy, only then you can build a decision tree, otherwise not. You don't have to draw something like that, data structure. No, there's no data structure here. You have to calculate the entropy, and then you have to calculate the IG, and only then based on the values of those measures, you can decide what you have to do next. Anyhow, let's take this. I am stopping, okay? And I will start this calculation in the next lecture. If I will start it now, maybe it will take 10 minutes, and then we will very close to Aftara. So next time, in the next lecture, try to